let's use the half angle formula to find the sine of 105 degrees. Well, 105 is half of 210. So you're thinking, why does that make it easier? Well, because 210 is 180 plus 30. So the reference angle for 210 is 30 degrees, which is special. So that's why we do it. So sine of 105 degrees is the square root of 1 minus cosine of 210 degrees divided by 2. And we take the plus here because we know that 105 is in quadrant 2. And in that quadrant, the sine is positive. So that tells us that's a positive square root. So cosine of 210 is negative cosine of 30 because 210 is in quadrant 4, so the cosine is negative, so it's negative cosine of the reference angle. That's special, so I get negative root 3 over 2. Great. Okay. Plug that in here, and I get 1 plus root 3 over 2. Little simplification, and I wind up with the square root of 2 plus root 3. So 2 plus root 3 itself, take the square root of all of that. So the line, the overline goes over everything, and divide everything by 2. And that gives us a formula for sine of 105. Questions? Okay. Oops. I thought I was going to get a different solution. So we could have done this using the sum of two angles, right? Sine of 60 degrees plus 45. That also would give it to us. Okay. So we didn't have to do it this way. Let's do another example. Let's take the sine of 5 pi over 8. Well, that's 5 pi over 4 divided by 2. Now we really have to use the half angle formula. You can't get 5 pi over 8 by adding and subtracting special angles. You just can't do it. So we really have to use the half angle formula. So this is tangent of 5 pi over 4 all divided by 2. Using that, one of those alternate, using, I guess, this formula for the half tangent of the half angle. So let's plug that in. 1 minus cosine of 5 pi over 4, sine 5 pi over 4. So 5 pi over 4 is, where's that going to be?
That's 180 plus 3.
180 plus another 45. So it's pi over 4, 2, 3, 4, 5. So it's pointing down to the left. So it's in quadrant 3. So both the sine and cosine are negative. And it has, its reference angle is 45 degrees. So they're both going to be negative root 2 over 2. So plug that up here. And plug that in the bottom here is, it's missing. Why is it missing? It should be good. It might be the animation, and the animation is messed up. Okay, that's fine. Okay, it's all right. All right. So there should be a root 2 over 2 in the bottom here. Simplify it, and I get 2 plus root 2 over minus root 2. Multiply both sides by root 2. Do a little simplification. And we get minus root 2 plus 1. So that's one way of doing it. We could have used the other formula. Oops. All right, now the animation is. We could have used this one instead. Actually, the animation, I should have done that first, but that doesn't matter. Okay. So we'll use this formula instead. And 5 pi over 8 is in quadrant 2, which means the tangent is negative. So I take the negative square root of all of that, and I get cosine of 5 pi over 4, which we already figured out is minus root 2 over 2. So plugging that in, doing a little simplification, we get this. And now I do the same trick to simplify the inside of the radical here. So multiply both sides of the fraction by 2 plus root 2. Oops. And, okay. Sorry about the animation. That's messed up. Here's the complete slide. Simplifying, I get the square minus the square root of 3 plus 2 root 2. So it looks like I got two different answers for the same function. So this, I get minus root 2 plus 1. And for this, I get minus root square root of 3 plus 2 root 2. They look different. Are they really different? So actually, they're not different. They're the same. You can convert one to the other. And this is one of those things where there's not necessarily a direct way of seeing that they're the same. You just have to sort of try manipulating one and getting it into the form of the other. So, well, how can we see? Well, maybe we can't even do that. But how can we see that they're equal? Well, they're both negative, okay? Well, that gets us a little bit closer. But, so, here's the trick. Let's square both of them. Let's take the square of both of them. They're both negative. If they're both negative and the squares are equal, then they have to be equal. The only time squares can be equal and two things would be different is if one was positive and the one was negative. But since they're both negative, if their squares are equal, then we know that they're equal. So the trick is to square both of these and see that their squares are actually equal. The advantage of that is when you take the square of this, you get rid of that outer square root sign. So if I square both sides, so I see if these are equal. I square both sides to see if the squares are equal. And here I'm left with just 3 plus 2 root 2. And here I square this, and lo and behold, when I expand that out, I get 3 plus 2 root 2. So the squares are in fact equal. So these happen to be equal, but there's no easy way of actually taking one of these and manipulating it around to get the other. You only see that when you take the squares of both of them and notice that they're both equal. So A squared equals B squared implies A equals B, provided that A and B are either both positive or both negative. Okay, in this case, they're both negative. Well, we actually ignored the minus sign, so it was positive. That's fine. Same thing. All right. Good. So, new topic. So we're done with half-angle formulas. Trigonometric equations. So we'll see some ones that are a little bit more sophisticated than the ones we saw yesterday. But these are all set up, they're kind of tailor-made for an easy solution. So, in some sense, this is kind of cheating. In the real world, if you were just given some random trig equation, it would not be easy to solve. In fact, it may not be possible to solve exactly. But these trig equations are solvable. And it's good at least to see, if you're given some trig equation, if there's some tricks that you can use to actually solve it, because it might be actually solvable. So one of these things is just to recognize when you can solve something. So here are some tricks to solve some trig equations. Let's find all solutions to the equation cosine of x equals 1/2. So we did something like this yesterday. Except now what I'm asking for is all solutions. And there are going to be infinitely many of them. So what is a solution for this? Shall we use the unit circle method? Tell me what to do. Draw the unit circle. Okay. the unit circle. Now what?
Draw the line x equals 1/2.
Okay. Draw the line x equals 1/2. That will be a vertical line. Okay, then what?
Where it intersects with the unit circle.
Look where it intersects with the unit circle. It intersects the unit circle in 2 spots. Now what?
The origin of the line.
Draw the lines to the origin. These are the terminal sides of the 2 angles that you get to make that true. So that's going to be 1/2. That's going to be 1. So then what? Special angle? Yeah. Sure. So that's 60. And what's that? Minus 60. That's fine. So you get pi over 3 minus pi over 3. These are the only 2 terminal sides you can have. But you have infinitely many solutions because you have these 2 angles, but then you have everything that's coterminal with those. So you add or subtract whole revolutions. All right. So pi over 3, or 60 degrees, is the solution. So this is a solution. So take the top point for a second. This is a solution, and then everything coterminal with it is also a solution. So pi over 3 plus 2 pi, pi over 3 minus 2 pi, plus 4 pi, minus 4 pi, and so forth. Okay, you get infinitely many solutions this way, just for this one, on behalf of this solution. Well, to express an infinite family like this, it's you have this regular property here. So we're going to express it as follows. It's pi over 3 plus 2n pi, where n is any integer. So 2n pi is n revolutions. So n can be any integer, positive, negative, or 0. So that's how we express this infinite family of solutions. We just say n pi over 3 plus 2n pi. So let's simplify it for various n. If n is 0, I just get pi over 3. If n is plus or minus 1, plus or minus 2 pi, and so forth. So I can put it that way. So that is the best answer. It's exact, and it tells you what each solution is for this point up here. But okay, so here's the graphing method. We also get another point here by symmetry. Sorry, no, these are all the points that were terminal with it. We get also this point, which is, well, it's coterminal with this, but it's actually on the other side. It's this plus a complete revolution. So it's actually 300 degrees, or 5 pi over 3, which is coterminal with minus pi over 3. Take everything coterminal with that. There we get our minus pi over 3 right there. Okay, so you could take, say, 5 pi over 3 plus 2n pi, or any number of complete revolutions. This will also include minus pi over 3. And in fact, this is equivalent to saying minus pi over 3 plus 2n pi. You get the same family. You just shifted the indexing by 1 revolution. All right. So, questions on that? So, finding all solutions, you have to express it, since there are infinitely many, you have to express it by some regularly spaced families of solutions. Ones that are all coterminal. All right, so I'm going to skip all of this. This is not necessary. All right, so in general, this summarizes kind of what we did yesterday and just now. To solve an equation of the form some trig function of x equals some constant b, so you're solving for x, find all solutions in one period of the trig function. So P is the period of the trig function. Find all solutions in a single period. That period might be 2 pi if it's sine and cosine. It's pi if it's tangent. And then for each solution you get, each solution contributes to a series of solutions by adding integer multiples of the period to the solution you get. So if theta is a solution, then theta plus n times the period is also the solution for any integer n. Okay. In step 1, you can use the graphing method, use reference angles, or, not written on the slide, you can use the unit circle method to find it as well. All right. So let's take this and apply it to here. Sine of x is root 3 over 2. Well, what's the period of the sine function? 2 pi. 2 pi. It repeats every 2 pi, and not less. So that's 2 pi. So first we find all the solutions in the range, say, 0 to 2 pi. Unit circle method. So y is root 3 over 2, horizontal. It actually goes to the same point we found earlier, and also goes to this point. Okay, which is what? Well, that's going to be 60. The reference angle is going to be 60 again because of symmetry. So that's going to be 120, or 2 pi over 3. So the solutions here in the period 0 to 2 pi are going to be pi over 3 and 2 pi over 3. Here's the graphing method. We'll also give that to you. Okay. Special angles again. Yada yada. Okay. 2 pi over 3. Now we just add all the other solutions are going to be coterminal with these. So we just include multiples of the period for each type of solution. So all solutions are pi over 3 plus 2n pi, or 2 pi over 3 plus 2n pi, for n is any integer. So that's the final answer. All right. Okay. Cotangent of x is minus 1. Well, you could use the graphing method. What is that? What that is? That's hard to say. It's hard to look at and tell what it is. It's a special angle. That helps. It's actually 3 pi over 4. If the cotangent, so the tangent of x is 1 over the cotangent of x, which is 1 over minus 1, which equals minus 1. So the tangent of x is minus 1. So using this approach for the tangent of x, what do you set the slope to be? Minus 1. So it just cuts those quadrants evenly. And so slope equals minus 1. And so I get two angles. I get that one and I get that one. If I am in the interval, if I'm in the interval 0 to pi, which is the period of the cotangent function, then this is the only solution, and this is then going to be 3 pi over 4, which is 135 degrees. Okay. Because this is in the range 0 to pi. That's the period of the cotangent function. This over here is minus pi over 4, right? But now I don't need to include this explicitly because it's going to be included anyway. when I take the infinite family of solutions. So the solution I get here, well, to make a long story short, is I get minus 1. I'm sorry, I get 3 pi over 4. So x1 is 3 pi over 4. So all solutions are going to be of the form 3 pi over 4 plus n times pi, because pi is the period, not 2 pi. So that already includes minus pi over 4, because you take 3 pi over 4 and subtract pi, and that gives you minus pi over 4. Yes?
Subtracting all the way up to 3 pi over 4, I just understand the plus n pi.
Plus n pi, okay. So the period of the cotangent function is pi. So it looks like this. Here's 2 pi. So the cotangent function repeats itself every pi. So every solution you get in the range from 0 to pi, you repeat in evenly spaced intervals of pi. That's why it's plus n pi. Okay.
What's the notation for infinitely many solutions to a given?
What,
I consider it a notation to infinitely many solutions to a given problem.
It is a notation for expressing infinitely many solutions to a problem. Yes.
It was on the last slide. Verbatim.
I haven't been to the last slide. You catch me cheating? No.
It's cheating if you look at the slides in the past. I just want us to think you're clever.
All right. Let's solve this equation. Well, I'll start you off, and then we'll abort.
That generally happens.
Sine of 4x plus 3 equals 5. So what would you do first? You just get sine x on one side, right? So sine x is 5 minus 3 is 4. Sine x is 5 minus 3 is 2. Divided by 4. Sine of x is 1/2. This now, we know how to do this already because we've done this a few times. So I'm going to stop here and not do it, and just leave it to you. There are special angles that give this to you, and you get an infinite family of solutions. Let's do part B, which looks a little more fun. Now you've got that is equal to 0. So in this case, the thing you should do is factor it. If you've got one side equaling 0, try to factor the other side. So I got the product of two things, and if the product of two things is 0, that's true just in case either one of them is 0. So we get two families of solutions. We get one by setting sine x equal to 0, and we get another by setting 2 sine x plus 1 equal to 0. This gives you sine x equals 0. Draw the line y equals 0 through here. You're going to get 0, and you're going to get pi, and then everything coterminal with that. So you're going to get 2 pi, 3 pi, 4 pi. You're going to get multiples of pi. That's sine x equals 0. Sine x is minus 1/2. Draw the line y equals minus 1/2 through here. And you're going to get that as a solution, and that as a solution. That's minus pi over 6, and that's minus 5 pi over 6. Special angles again. Okay, and then everything coterminal with those two. So let's not draw this out. These solutions are multiples of pi. This is, you can see this in the graph, because that's where the sine function crosses the x-axis. Pi, 2 pi, 3 pi, minus pi, and so forth. For the other solutions, well, okay. Instead of minus pi over 6, we used 11 pi over 6, which is coterminal with it. Because this is actually in the interval 0 to 2 pi. And then we just added multiples of the period. And then for the other solution, 7 pi over 6, that's in the interval 0 to 2 pi, so it's coterminal with that one. And we add a whole number of revolutions, and these will get you the minus pi over 6 and the minus 5 pi over 6 as well. So this is the complete family of solutions for this particular equation. Questions? All right, let's try another one. What would you do with that?
On every time the quantity is sin x plus 1.
You know, you can factor the left, but you don't have 0 on the right. You only factoring really only helps you if you have 0 on the other side. So put 0 on the other side. Yeah, subtraction on both sides.
What was that?
Now try to factor this, and it does factor. 2 sine x minus 1 times sine x plus 1 is equal to 0. So again, now this reduces to 2 separate equations and linear equations involving sine of x. And now I go back to things I did before, like in part A, where I just isolate sine x on both sides. So here I get sine x equals a half, or sine x is minus 1. Sine x equals a half. Line y equals a half goes through here. It's going to hit here, and it's going to hit here. What's that angle? It's a special angle, 30 degrees or pi over 6. And this is going to be a supplement. So it's 180 minus 30 is 150 degrees, 150, or 5 pi over 6. And then everything coterminal with those, so, plus 2n pi for each. So that's going to be this one. How about sine x is minus 1? Negative 1. It grazes, tangent to the circle, it grazes just in one spot. What is it?
0, or y equals 0. Or I mean, x equals 0. So,
Right, so x is going to equal 0, but in particular, the angle
90 degrees.
is,
Pi over 2.
now it's minus 90 degrees. Or, so it's minus pi over 2, or if we want to be in the range 0 to 2 pi, because that's the period. Sorry? 270 degrees, right. Or 3 pi over 2, either way. Yep.
So when using this notation, you can use any of those solutions, correct? You could use negative pi over 2.
Absolutely.
And you still
Yeah, so because, I could have said minus 5 pi over 6 plus 2n pi, you get exactly the same family. You've just shifted the initial reference angle over. And I could have said minus pi over 6 there. That's fine. They're both correct. All right, so here, to make a long story short, this is pi over 6 plus 2n pi, or 5 pi over 6 plus 2n pi. We got those from there. And this is going to be 3 pi over 2 plus 2n pi. Because this is, to get down here, you have to go 3 pi over 2. 270. Okay. And this would also be equal to minus pi over 2 plus 2n pi. The plus 2n pi kind of obliterates all those distinctions. All right. Ready for another one?
Ready or not?
Ready or not? We got it. Part D. Cosine square root of x plus root 2 cosine of x plus 1 is 1 minus cosine squared of x. Okay. Now, that you might be tempted to turn that into sine squared of x, but that would not be good, because now you have two different trig functions you have to contend with. Try to get all the trig functions the same, and then just treat the trig function as like a new variable. Okay, and manipulate it. So get everything over to the left, get 0 on the right, and try to factor. That's kind of how we're doing things. So if I'm going to get 2 cosine squared x, the ones cancel, that's nice, plus root 2 cosine x. Now factor this, take out a cosine x times 2 cosine x plus root 2. So you get two solutions here. Cosine x can equal 0, or this thing can equal 0, which is equivalent to cosine x equaling minus root 2 over 2. That looks a lot like a special angle.
It's 45 degrees.
Well, its reference angle is 45, but cosine is negative, so
225.
it's got to be over here. So it's that, and it's those two things right there. So it's 3 pi over 4 and 5 pi over 4. Okay. So that gives you that 3 pi over 4 and 5 pi over 4 plus 2n pi, the usual. And cosine of x is equal to 0. Well, we draw the line x equals 0 through here, and it hits right there, and it hits right there. So that's pi over 2 and 3 pi over 2. But those differ by pi. So, in fact, you get pi over 2 plus multiples of pi. So this includes 3 pi over 2 in it. So I don't have to give two explicit families. I can combine those into one. So if you had said, say, pi over 2 plus 2n pi and 3 pi over 2 plus 2n pi, that's correct. It's just not simplified. The fact that you can merge these into one family over here, that's simpler. So that's preferable. Okay? Questions? Yeah, so if these things differ by pi, then you can always just combine these into one of them plus multiples of pi instead of 2 pi. All right, let's do another one. Okay, again, we'll set it up and we'll talk through the final solution. So here, 2 cosine squared, 2 cosine to the fourth. 3 pi, 1. All right. Well, this factors into that. This factors. Well, I guess I can solve for this already. Solve for cosine squared of x. Cosine squared of x is 1/2. So cosine of x could be either plus square root of 1/2 or minus the square root of 1/2. So that's plus root 2 over 2 or minus root 2 over 2. So cosine x could be either of those. Or, solving for cosine squared x here, I get that equal to 1. Take the square root of both sides. Cosine x could equal plus or minus 1. So where on the unit circle are all these points? It's cosine, so when I draw the dotted line, is it going to be horizontal or vertical? It's going to be vertical. It's the x coordinate. So plus or minus root 2 over 2 over root 2. That's going to be here. That's going to be there. Plus or minus 1. That's a plus 1, and that's a minus 1. So this is x equals minus 1. X equals minus root 2 over 2. X is equal to plus root 2 over 2. And x is equal to 1. So it hits here, 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 here. Okay. So 6 different terminal sides. I get an angle 0, angle pi. I can combine those into one family as how? Pi plus n pi, or even simpler than that? Just 0 plus n pi, or just n pi. Okay. So here, I get n pi for this one and for that one. Okay. Here, these are actually all special angles, right? Pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4. So I got one family, n pi. I can take pi over 4
Yeah, you can just use a
plus 2n pi, 3 pi over 4 plus 2n pi, and 5 pi over 4 plus 2n pi, and 7 pi over 4 plus 2n pi. Okay, so you can certainly do that.
or you can say pi 4.
Yeah, some of these can combine into one in the single family.
First and third and second and fourth.
Yeah, so these two, since they differ by pi, just change this into, say, pi over 4 plus n pi, not 2n pi. And that will give you pi over 4. It also includes 5 pi over 4.
Can't you just give it a period? Half.
Hmm?
Can't you just give pi 4 as a period of n?
Yeah, you could do that too. Okay. So you can combine these. I'll do that. I'll get it. This is 3 pi over 4 plus n pi. And Captain Hall, is this Captain? Is it? Yeah.
Yes.
Captain Hall suggests that you can actually even combine these further and say that this is, you could take pi over 4 plus n pi over 2. And that includes 3 pi over 4 because those differ by pi over 2, which is half the period you start with. So this, in fact, that's good. So we got this, and we get those. Those are the two consolidated into two distinct families of solutions. Very nice. Questions? All right. I'm not too worried if you don't do that. Because it's okay. You just have 2n pi everywhere, but I guess that's fine. All right. So, to make a long story short, I'm just going to skip through this because we already did it. All right. Now I've got a 3x here. So, whatever solution I get for 3x, I just divide by 3. Okay, so I'm not going to worry about that. Same thing, and instead of anything I get for x over 5, I multiply by 5 to get the solution for x, so I'm not going to worry about that. So just zip through these, don't worry about it at all. Plenty of time. Okay, fine.
That's which graph?
Let's try this one, because now we've got two different trig functions. We've got a cosine and a sine. So the usual way to do this is try to get all the trig functions the same. In this case, it's easy because you can take cosine squared and replace it with 1 minus sine squared. And all of that gives you a 3 minus 3 sine squared equals 0, or 3 sine squared x equals 3, sine squared x equals 1. So sine of x is plus or minus 1. And then go from there. You won't bother. Sine of x equals cosine of x. Okay. So here, if you divide both sides by cosine x, then you get tangent of x on the left, and you get 1 on the right. Now, when you divide by cosine x, you assume that you only do this if cosine of x is different from 0. You can only divide by something that's not 0. So when you divide, you always have to ask yourself, is my assumption ignoring a possible solution? So you should always go back and ask yourself, what if cosine x is equal to 0? Does that also give you a solution? In this case, it doesn't. Because if this is 0, then x has to be, if cosine of x is 0, x is going to be either pi over 2 or 3 pi over 2 or something coterminal with it. But if this is 0, if these two are equal, then sine of x would also have to be 0 at the same time. But sine of x is only 0 here and here. So they're never 0, they're never both 0 simultaneously. So if cosine of x is 0, that does not give you any solution. So it's safe to divide by cosine x because you know that cosine x equaling 0 is not going to give you a solution. So assume it's non-zero, divide by cosine of x. That gives you tangent of x equal to 1. And now this, we've done this before. It's some trig function equaling some constant, and so we won't bother. Just draw a line with slope 1, see where those angles are. Okay. Or do the graphing method, which is probably not as good. But you get pi over 4, which gives you a slope of 1, plus n pi, because pi is the period of the tangent function. If you graph sine x and cosine x, this is exactly the x's where they cross. So right here and right here. So by symmetry, that's pi over 4, and that's going to be 5 pi over 4 and so forth. And equally spaced points here differing by pi. Okay. Sine of 2x plus cosine of x is equal to 0. So what would you do there?
Double angle.
It's a good exercise. Yeah, so use the double angle first. So sine of 2x you can write as what?
2 sine u times cosine u.
Yeah, so in this case it's
Or x.
2 sine x cosine x. Then what would you do?
Cosine x. So you would set basically 2 sine of x equals 0.
So it's 2 sine it. You're dividing by cosine x. You gotta be careful here. So let's do this.
You just factor out cosine.
Yes. Now, you can divide by cosine of x, provided you then go back and say, does cosine x equaling 0 give solutions? And in fact, it does. Because if cosine of x is equal to 0 here, then that satisfies this equation. So, but it's easier just to not divide because that brings in assumptions. Here, you can factor instead. So factor out a cosine of x. And now just take each factor separately and solve as you know how to solve. So I'll do this for you. Let's do this one. Cosine of 2x plus sine x is equal to 0. Cosine squared x minus sine squared x, or just to make a long story short, there's a formula just involving sine squared x here. It's 1 minus 2 sine squared x plus sine x. So now everything's in terms of sine, and I get that, and I believe that factors. Negate both sides, so that the leading term is positive. If it factors, it's got to look like that. Okay, great. And so, go on your merry way. Oops. Yeah. So in the case if you have different angles, you want the angles to be the same. And then maybe you also want the trig functions to be the same. Or if you can factor something like this, each factor has only one type of trig function, and that will also work. All right.
Can you go back?
Sure.
For the x equals, can you make that x equals 4? What is it? 4 pi over 6? To sum up all those? Or keep adding 4 pi over 6?
You mean 2 pi over 3? I don't think so. No. So let's actually picture where these are. So pi over 2 is where? It's right there. 7 pi over 6. that's, oh, maybe, yeah. So this is 6 pi over 6 plus another pi over 6. It's down there. And then 11 pi over 6 is over here. They are actually evenly spaced, aren't they? So, yes, so then you are in fact correct. You can convert this into one family. What would that family look like?
Pi over 2 plus 2/3 pi? Or 2/3 n pi?
Yeah. Good. One family does it. Nice. All right, because, yeah, so 1/2 plus 2/3 is, well, that's 3/6 plus 4/6 is 7/6. Yeah, so that gives you 7 pi over 7. Okay. Very good. You're all smarter than I am. All right.
Can I just
Yeah?
have that in the plan?
You need something in writing?
Yeah, I'll take that.
Okay. Do I want to do any of this? Probably not. It's getting kind of old now. I suppose here, I don't know about that. I'll just forget that. For here, I've got a 4t and a 2t. The thing about it is here, don't bother getting things in terms of t, just a t. You might as well just use 2t. Because you can convert this into cosine of 2 times 2t and just use the double angle formula. Now, everything is in terms of 2t. You've got the same angle. It's not t, but it's the same angle. So the solutions you're going to get here are going to be solutions for 2t, and then just divide by 2 at the end. 2t. Okay, fine. So we get all of that. We divide by 2, rather. Okay. All right. What? Oh, yeah, there's another identity. Okay. Cosine x plus cosine y is equal to 2 cosine x plus y over 2 cosine x minus y over 2. You can get all of this using angle addition formulas and half angle formulas or double angle formulas. But we're not gonna derive that, and I'm gonna skip this slide because this is getting kind of old and it's getting toward break time. So let's see what's next. I think yes, this will be the final topic. So we'll take a break and come back and solve some triangles. This is what we've all been